Okay, let's try to solve another example. I have here, find the area of the region bounded by the curve x equal to y squared and y is equal to x squared. Take note, these are parabola since we have a second order function, and however, they are different in orientation. Since if you try to plot x is equal to y squared, or we can say that is y squared is equal to x, it is in the same form with what we know, the general form of the parabola, in which we have y minus k squared is equal to 4a x minus h, in which we know that if we plot this general form, we have our curve which is opening leftward or rightward, since this could be positive or negative, but we are sure that it is opening rightward or leftward. But if it is positive, we have a parabola which is opening rightward. So if it is positive, now take note, this one is positive, okay, since we don't have negative at this point, so therefore we are sure that it is concave to the right. Now the vertex here, we know that our k and our h is equal to 0, so therefore our origin here is at 0, 0. Okay, so at this point, so or this can be the graph of y squared is equal to x. Now for y is equal to x squared, or we have x squared is equal to y, it is the same form with x minus h squared is equal to plus minus 4a y minus k, in which we know that if we plot this general form or equation of the parabola, we are certainly sure that this is concave upward or downward, since we have our x here being raised to the 2. So therefore, we sure that this one is opening upward since this is positive, and the vertex is at the origin since we have h and k which is equal to 0. Okay, that is equal to 0, 0. Okay, so now let's try to plot this graph accurately in our Cartesian plane. Now let's try to plot this first, y squared is equal to x, so we can create a table with x and y table. If we set our x here as equal to 1, let's say that's 1, our value of y could be plus minus 1, correct? Since we have y squared is equal to 1, y is equal to square root of 1. Take note, it has two possible roots, positive and negative, so we could have positive 1 and negative 1. So therefore, we have, if we have x is equal to 1, our y is positive 1 at this point, and y is negative 1 at this point here. Okay, so we can now draw our parabola in which our vertex is at the origin, and we know that it is acting rightward, so we have this parabola, this one. So this is y squared is equal to x. And then let's plot x squared is equal to 1. Again, the vertex at 0, 0 or at the origin. So let's set here as, let's say our y is equal to 1. Then we have x squared is equal to 1. So x is equal to plus minus square root of 1. Then we could have two values of x, which is positive 1 and negative 1. So we have positive and negative 1. So let's plot this curve. We have, when y is equal to 1, we have positive 1. So at this point here, and negative 1. So at this point. So we have, so this is the curve for x squared is equal to y. Since the area here is being bounded by these two curves, so we will be computing the area of this region. Okay, that shaded region there. So in computing the area, we need to determine first their point of intersection. Now we know that their point of intersection are first at the origin, take note, so therefore they have point of intersection at 0, 0. Okay, and the next, their point of intersection is at this point, So how are we going to compute that point? Okay, so we can use substitution method in determining the common coordinates. We know that y squared is equal to x squared is equal to y. We know that their value of y are equal and their value of x's are also equal. So we can use either of these two relationship. Okay, let's try to use y is equal to y, and we know that y for this curve is square root of x, correct? This for equation. Now, the value of y here for this curve is equal to x squared. Okay, so by further simplifying, then we have square root of x is equal to x squared is the same as x is equal to x squared raised to the 2, and this gives us x equal to x raised to the 4th. Then we can cancel x. We have x cubed is equal to 1. Okay, so we have x is equal to cube root of 1. This gives us x is equal to 1. That is the point of x coordinate of the point of intersection. Now for y, we can use either of this equation. So let's set the value of x equal to 1 for in the either of these two. We have y squared is equal to 1. Let's use this equation. Then we have y is equal to 1. So therefore, their point of intersection is at coordinates 1, 1. When our x is equal to 1 and our y is equal to 1. So we have this point here which is 1, 1. So now we can compute the area. Now in computing for the area, we need to draw a vertical strip or horizontal strip. You can use either of the two, but since from the previous example, we use vertical strip, now let's try to use horizontal strip to this one. Now for horizontal strip, we just need to draw a horizontal rectangular strip. Okay, that one. So in our horizontal strip, we know that our area of the rectangle is equal to just the length times the width. Now for this horizontal strip, we have our length here, which is x, and our width here, which is dy. That's the derivative of y. Again, since our width here varies with our y axis or y coordinates, and it is very small, or let's call it infinitely small, and thus we set that as the change in the y. Okay, so therefore our area is x dy. Now, as what we can see here, our horizontal strip is floating. If we try to create a rectangular, like for example, floating to the right, let's say the coordinates at this point is 4, 3, and the coordinate at this point is 2, 3. Okay? Now we can compute the height x here, or this is the height of this rectangular strip, by just subtracting this height. Let's say that's x sub 2, and this height here, let's say that's x sub 1. Okay, that's the dimension of this rectangular strip, which is x. And we know that x sub 2 here, that is the distance from the y-axis to this point, and we know that the x coordinate at this point is 4. So we set that x2 is 4. Now at this point, we know that the x coordinate, which is the distance from the y-axis to this point, which is 2, correct? So let's say that's 2. So therefore, our value of x here, or the height of this horizontal strip, which is just x is equal to x sub 2 minus x sub 1, correct? So x is equal to 4 minus 2, and this gives us 2. So therefore, this height from this point to this point is 2 unit. Now, similarly, for this horizontal strip, we can say that the x here is just equal to this coordinate, let's say that's x sub 2, minus this coordinate, let's say that's x sub 1. So therefore, we can say that our x here is just equal to x sub 2 minus x sub 1 and then the width dy. Okay, so we can now integrate it. So x sub 2 minus x sub 1 dy. Now, our limit is from, now take note, we are deriving it with respect to y, so therefore our limit should be along the y-axis. So therefore our limit is within this range. Okay? So our limit here is from 0 to our y here, which is 1. That is the y coordinate at this point. So therefore our limit is from 0 to 1. Okay? Now, again, since we are integrating with respect to y, so we should transform this variable x into a function of y. Now, our x sub 2 here, let's check at the graph. Our x sub 2 touches this curve, okay, or this blue curve here. And we know that the function or the equation of this curve, this blue colored curve, is equal to x squared is equal to y. Okay, so therefore, we have our x sub 2 here. That is, if we could express it as a function of y, we have x is equal to square root of y. Okay, that is our function. And this is our x sub 2. Again, since our x sub 2 here touches this curve, this blue one curve. Okay? And our x sub 1 here touches the green curve. Our x sub 1 here, and this green curve here, has a equation which is y squared is equal to x. So therefore, our x sub 1 here is equal to y squared. Okay? That is the function of y. Instead of using function of x, since again, we are deriving it with respect to y, okay, so therefore, we need to have a function of y rather than a function of x. So let's convert this x sub 2 and x sub 1 in our integration. We have the area is equal to the integration of 0, 1, and x sub 2 here, which is square root of y, x sub 1 here, that is y squared, and then derivative of y or dy. Then we integrate them separately. We have, let's say, y raised to 1/2 the integration of 0 to 1 dy minus the integration of y squared dy from 0 to 1. We have here 2/3 y raised to 3/2 minus 1/3 y cubed, limit from 0 to 1. By evaluating this formula, we have 0.333, that is square units, or that is 1/3 square units. So we have this final answer, or the area of this region. Okay, so we use horizontal strip. Now you can try to use vertical strip to this one. So the same procedure, we just set our height there, that is y sub 2 minus y sub 1. And the equation or the function of y sub 2 with respect to x depends on where our y sub 2 touches on the curve. Okay? So 0.333, or that is equivalent to 1/3 square units, is our answer to this problem. I have prepared new example in the next video.